We are talking about two-dimensional systems and making phase portraits. So getting qualitative information about phase portraits. We started with looking at linear systems, and now we're going to start looking at nonlinear systems, but kind of piecing it together with little linear pieces. We're going to look for fixed points and linearize about fixed points, and then construct phase portraits and learn something along the way from there. So let's do it. It's fixed points and linearization. This is section 6.3 specifically of Strogatz. So I want you to think of what we've written as a two-dimensional system, autonomous, with two scalar variables, x and y. So we've got x dot equals f of x and y. That's a scalar, and y dot is g of x and y, another scalar function. Let's suppose that this has a fixed point. We'll call that x star, y star. So that means that f of x star and y star is equal to 0, and g of x star, y star is equal to 0. That's the condition that you would write to find fixed points. Look for points x star and y star that satisfy that both of these scalar nonlinear equations equal 0. So the next step for linearizing is we want to transform to some new coordinates where the origin is the fixed point. So we're going to choose new coordinates. I'll call them u, which is x minus x star, and v, y minus y star. So in some sense, all we've done is we've translated to new coordinates where the origin, that is u and v, equal to 0, 0, is a fixed point. Because if u equals 0, that means that x equals x star, and if v equals 0, that means u equals u star. So we will then write out the differential equations, these differential equations up here, but write them in terms of u and v. So if we take the derivative of u, right, du dt equals dx dt. So this might be emphasized if up here I wrote that u is a function of time and x is a function of time. X star is not, it's just a fixed point. So same here. What is v? V is still going to be a variable, something that changes in time, but y is not. I mean, y is and y star is not. So that means when you take du dt, it's the same as dx dt, but we'll use a Taylor series expansion, right? So if we write du dt equals dx dt, we'll write that as u dot. Well, this will be f, but now we're going to write, instead of x and y, we'll substitute in how you would write x in terms of u and x star. So this is f of x star plus u and y star plus u. All right, that's just by substituting in this change of coordinates, but rewriting x equals u plus x star and flipping it around. So now we do a Taylor series expansion. We've done a one-dimensional Taylor series expansion when we analyzed the 1D ODEs. Now we're just going to do a 2D Taylor series expansion. So a 2D Taylor series expansion is that you evaluate f at the fixed point, then plus u times partial f partial x evaluated at the fixed point. So we might write x star y star plus v partial f partial y evaluated again at the fixed point, x star, y star, plus higher order terms. And I'll just write that as HOT. So this would be, for example, things that have u squared or v squared or u times v, or even, cubic and higher. Okay, so that's u dot. But what is this? Because we have a fixed point, f of x star, y star is 0 because fixed point. So there we go. And we could do the same thing for v dot. V dot is going to be dy dt. So I'll just jump to doing the Taylor series expansion and then substituting in, because of the fixed point, that g x star y star equals 0. So what are we left with? We're left with u partial g partial x evaluated at the fixed point plus v partial g partial y evaluated at the fixed point plus higher order terms. We are assuming that we're only going to be looking at small distances away from the fixed point. So that means u and v are small. So these higher order terms, the quadratic terms, are extremely small. Right? We've got something that multiplies u here and something that multiplies v here. But if we have something that's u times v, or u squared or v squared, or any nonlinear term in u and v, it'll be extremely small. So that's the justification. We'll summarize u dot and v dot, write it in matrix form. U dot v dot equals partial f partial x partial f partial y. Down here is partial g partial x partial g partial y. And this multiplies u and v plus, we'll just write higher, if you want, higher order terms. So this matrix that I'll call A, this is called the Jacobian matrix of the vector field evaluated at the point x star, y star. So I might, just to remind us that this is at x star, y star, I'll put it down here. So even though we're writing partial derivatives, don't view these as functions anymore. For the matrix A, we're evaluating those at a specific point. So these are just numbers in here. They'll be constants. So A is commonly called the Jacobian matrix of the vector field that had components f and g. We're evaluating this at the fixed point. It is a 2x2 constant matrix. Now, since the higher order terms are very small because they're from multiples of u and v, nonlinear in u and v, we can ignore them in many cases. We can ignore them if you think of the diagram we had before. You can ignore these higher order terms when we're off of the borderline cases. Let me remind you of what that diagram looked like. We can ignore the higher order terms. What do I mean? We can ignore them. To get the qualitative dynamics near the fixed point, we can ignore the higher order terms away from the borderline cases from before. So I'll just put that diagram again where we plotted the determinant of A as the horizontal axis. And then up here, we called this tau. This was the trace of A. Borderline cases are all these thick lines. And inside, so to the left, when tau is negative, no matter what delta is, as long as tau is negative, these are saddles, fixed points. Then we've got up here unstable nodes. Down here, we had stable nodes. And then down here, stable spirals or stable focus. That's what some authors say. And up here in unstable spirals. Borderline cases where like these stars and degenerate nodes or the non-isolated fixed points, or probably the most common borderline case is along here when we have tau equals 0 and delta is positive. Those are centers. We'll talk about those today. So anything on the borderline means you're on one of the lines. If you're away from the lines, so if you're in one of these regions that fills, space, then the qualitative dynamics near the fixed point, even in the full nonlinear system, the qualitative dynamics is given by the linear system. So where we ignore the higher order terms. So qualitative dynamics in the full nonlinear system given by the associated linear system, right? U dot V dot equals A U V. And this is, of course, if we are away from a borderline case, but you'd have to evaluate the trace and determinant of A to know that. So let's look at some examples and go ahead and do this. And if you wanted to look in the book, this is example 6.31. We have x dot equals negative x plus x cubed. So this negative x plus x cubed would be f of x and y. And notice it's just a function of x here. And the y dot equation is negative 2y. So let's find all of the fixed points of this system and classify them according to this diagram up here. So how do we find the fixed points? Let's start with y dot equals 0. That implies that y equals 0. So for all the fixed points, y will equal 0. But then what about x dot equals 0? We can pull out an overall x, then it's minus 1 plus x squared equals 0. So this implies we either have x equals 0 or x equals plus or minus 1. The fixed points are 0, 0, 1, 0, and negative 1, 0. There's 3 fixed points. Let's look at the linearization near each of them. What we could do is calculate the Jacobian for this vector field for any general point x, y, and then plug in these specific points. So the Jacobian matrix, this vector field at any x, y, so not necessarily just a fixed point, you just take the partial derivative of each side. If you want, instead of writing it in terms of f, I'll write it this way: partial x dot partial x dot partial y dot partial x, partial y dot partial y. You write that out, and what do you get? This is negative 1 plus 3x squared, and then x dot does not depend on y, so that's a 0. And here y dot does not depend on x, so that's a 0. And then y dot partial gives us negative 2. This is at any general point, x and y. So now we'll evaluate at these specific points. At 0, 0, a equals negative 1, 0, 0, negative 2. I mean, we could automatically get the eigenvalues from this, but let's write it in terms of the trace and the determinant. The trace is what? Negative 3. And the determinant is 2. So hold on. We'll be in this stable node region, because what was that hyperbolic line? That was the case for tau squared minus 4 delta equals 0. And we're below that. So we're in the stable node regime. We have a stable node. And so we kind of have an idea of what the dynamics would look like near stable node. There's going to be some direction where things are coming in fast, coming in hot, and then some other direction that things are coming in less fast. And so there'll be, I may have the actual directions wrong, but this is generally what you're going to get, something that qualitatively looks like that. So that's what near the origin dynamics will look like that. What about the other points? We can lump the other two because x squared is the same for both, right? X squared is just equal to 1 for both. So what does that give us? At plus or minus 1, 0, a equals, what is this? Negative 1 plus 3. So we get 2, 0, 0, negative 2. The trace of a equals 0, but the determinant of a is negative 4. So going up here, trace is 0, determinant's negative 4. So we're somewhere definitely within the saddle region. We've got saddles. And we know what saddle points look like as well. There's going to be some direction where things are leaving, and then some other direction where things are approaching, and all other trajectories are sort of following one and then following the other nearby. So we don't have borderline cases. So that means in the full nonlinear system, this is the strategy. You want to kind of piece together what's happening near each of these points. So we know that there's saddle points. We've got this one and saddle point over there. So let's call this 1, 0, and that's negative 1, 0. And then the origin, 0, 0, is stable. And we expect that the nearby phase portrait is going to look something like these two figures. So what I'm going to do now is just show you what it looks like numerically. We could do more analytically to try to get at it. I just want to show you numerically. So there is an online phase portrait plotter. It's the only one I found. So I'll post a link to it somewhere. All right, so I'm going to type the negative x plus x cubed. You have to be careful here. If you put in any spaces, it doesn't work, and you won't know why. And there's -2 times y. And then I'll plot the phase space. It actually just plots the arrows. You get to choose what the display is. -2 to 2 in both directions. So it shows x and y. Now you just touch an initial condition and it numerically integrates forward and backward. So that's what that initial condition. Actually, now I'll go in quadrant 2 and just pick a few. Just sort of plot a few. So it's generating a phase portrait. And you can kind of see, oh, wow, near these 2 points, near the 2 saddle points, we have that saddle type behavior. And near the origin, we have stable node type behavior. So this is handy. The qualitative picture, if we just sort of sketch this, and there's other things we could have done. Like we could have determined that the y-axis is actually invariant. If you start on there, you stay on there, which means that arrows are kind of going in from there. And the x-axis is also invariant, right? You could tell that because, what do I mean by that? I mean that the x dynamics and the y dynamics are uncoupled. So if you're on one of the axes, you stay on one of those axes. That's one of the implications. And on the x-axis, things are kind of doing this. And we could plot other significant lines. So things are, actually the arrows are going the wrong way here. So things are coming in to go to this stable node, and then things are moving away from the saddles, which we can then describe something called a basin of attraction. Everything in this yellow region, which extends between x and plus is plus or minus 1, and then kind of going up to y goes to plus infinity and negative infinity. Everything in that band, this is the basin of attraction of the stable fixed point. And that'll become useful when we look at other examples. So we'll do another nonlinear example where x and y are coupled. X dot equals -y plus a x squared plus y squared. And y dot is x plus ay x squared plus y squared. So this has one parameter. It could be anything. It's real. So when we have a parameter, that means, oh, maybe this undergoes some kind of bifurcation. There's only one fixed point, and it's 0, 0. So we don't have to go to u and v coordinates. If we did the linearization, the second term of both x dot and y dot are nonlinear. So they're not going to show up in the linearization at the origin. So we can just immediately write what the Jacobian is. And Jacobian matrix are used interchangeably. So we might just say Jacobian. So we've got 0, -1, 1, 0, because this is -y. So take partial that, partial y. And then this just has x. It's linear term, so take partial that, partial x, and you get a 1. So that's what A is. So if we look at what it's got for the trace, it's zeros along the diagonal. So tau is 0. The determinant is 0 minus 1. So this is 1. So where are we? We're actually, if we go back up here, we're in that center. This would say we have a center. Well, centers are a borderline case. Now we need to be careful. If you have a borderline case, it means that the nonlinear terms matter. We could say this is a center. So borderline case, proceed with caution. Well, you don't have to proceed with caution, but coming to any kind of conclusions yet, the nonlinear terms are going to be important. So we can analyze this system by using a change of variables. This is just x and y, but that doesn't mean we have to be stuck with x and y. So here's x, here's y. We could write things in terms of polar coordinates. So if this is our point, we could use r and theta, the usual polar coordinates. So write ODEs in terms of the polar coordinates. You might say, why am I doing this? Well, I know how it's going to work out. So we'll use r and theta. X equals r cosine theta. Y equals r sine theta. We want to get differential equations So we want to get r dot and theta dot. So we could substitute in x and y and go from there. Another way we could go is we could write x squared plus y squared. We know that x squared plus y squared equals r squared. That's what defines r. And if you take the derivative of this, go d by dt on it, what will you get? You get x dot plus y dot equals r dot. Where's the factor of 2? There was a factor of 2 in each of the terms, so we just divided by 2. Now, if we substitute in what we have up here in the top for x dot and y dot, what do we get? So r dot equals x times, let me see what it is, minus y plus ax. And I'm going to notice that in these parentheses, this thing is r squared. So I'll just already substitute in r squared. What I would like is an ODE for r. So r dot equals some function of r and theta. So I've got that plus y times y dot, which is x plus a y r squared. And then expanding out more, what do I get? I'll get negative xy plus a x squared r squared plus xy plus a y squared r squared. These terms cancel out, and I'm left with a r squared x squared plus y squared. But oh, now I've picked up another r squared. What do you know? A r to the 4th. So this implies this was r times r dot. So this just divide by r. R dot equals a r to the 3rd power. So that's convenient. I mean, the way it works is I started with this and then wrote it in Cartesian just to make it look confusing. If you do the same thing for theta, you get theta dot is x times y dot minus y x dot over r squared. And it ends up just giving you, for this particular system, theta dot equals 1. So it's very nice when written in terms of polar coordinates. And it's worth looking at what each of these would produce. If we have a less than 0, that means wherever you're starting, the trajectory is going to shrink. In theta, it's going to be continuously turning around. So it turns around with a constant angular rate, spiraling in. So if you come back to the same theta, you're a little bit inside. And so this is going to continue until it gets to 0. For a greater than 0, you could probably guess what's going to happen. If we start with the same initial condition, this will go around and it'll be outside, and it'll just keep continuing and spiraling out. If we went backward in time, we would have something that's kind of emerging from the origin. So in this case, 0, 0 is unstable, but we had to look at nonlinear terms to see that. Here, 0, 0 is stable because everything's going in. And then the marginal case in between the two, a equals 0 means we just have that linear system. A equals 0 means that the radius doesn't change. Wherever you start, you'll just be on a circular orbit coming back to the same point, no matter where you are. So that's the common picture of a center. Here, this is also stable because if you start near the origin, you just sort of stay around it. This situation on the left, we might also call it an attractor or a sink. So I might put also known as attractor or sink. And this is also known as, it's the opposite of an attractor, is a repeller or source. And then the thing in the middle is just like a marginal case. From the linear analysis, we would have thought only this case in the middle is possible. But of course, it's not. That would have been if you were throwing a dart at a random value of A, you're not likely to hit 0. You're likely to have it's going to be negative or it's going to be positive. So in the space of all possible parameters of A, this is measure 0. It's one point on a line, but it's what the linear analysis would have told us. So that's why you've got to be careful for borderline cases. And borderline cases would also be called structurally unstable. The moral centers are very fragile, which means a general nonlinear term makes the fixed points no longer a center. What's going on, another word for fragile, it's related to the concept of structural stability. If we have something, if we have a system, I'm going back up to this diagram. If we have a system and it's in, let's say it's in this saddle regime, so it's like this orange point, any small perturbation to the vector field will still keep this a saddle. In fact, any of these regions, like the saddles, unstable nodes, unstable spirals, so on, that fill up an area, if you're in that area and you have a small perturbation to the vector field, it's not going to change whether or not you are, we're talking about infinitesimally small. You would still be in that same region. So if I have a point here that's in the unstable nodes, any small perturbation, I will still be an unstable node. That's not true for the borderline cases. The cases on these black lines, if you start there, you could have an infinitesimally small perturbation to the vector field that would move you off. So if I'm a center, an infinitesimally small perturbation will make me go into an unstable spiral or a stable spiral. And that's kind of what we see here. So this is related to structural stability. What is the effect of a infinitesimally small perturbation? So the borderline cases are not structurally stable. The center is a borderline case. The others are. This is also called, although it makes less sense, hyperbolic. If a point, fixed points are sometimes classified as whether they're hyperbolic or non-hyperbolic. All of those cases that are not borderline would be called hyperbolic. And that's related to, if you look at the real part of the eigenvalues, if you have eigenvalues that are off of the imaginary axis, then the fixed point is called hyperbolic. In this case, the eigenvalues were plus or minus I, so they're exactly on the imaginary axis. If you have something that is non-hyperbolic, you have to go to nonlinear terms. So a fixed point has any eigenvalues on the imaginary axis called non-hyperbolic fixed points. And it means you need to consider the higher order terms, in other words, the nonlinear terms, to determine stability. And we won't get into that yet. Be careful if you have one of these borderline cases. So this doesn't mean centers are completely irrelevant. If you study orbital mechanics, and let's admit it, most of the cosmos is determined by gravity and orbital mechanics. So orbital mechanics is very significant. And there, the dynamics can lead to centers. So these center type dynamics lead to periodic orbits. In fact, entire collections of nearby periodic orbits, which is kind of what a solar system is. So it's not irrelevant. That's just one example. There's other cases. In fact, at the most fundamental level, the dynamics are Hamiltonian. And Hamiltonian means that you've got some conservation of energy. When you've got things that have conservation of energy, you can get centers. So the very smallest things are governed by quantum mechanics, which can lead to periodic behavior and centers. That's more a philosophical thing. In the space of mathematical systems, centers are fragile. They can have influence in some mechanical systems.